Hello, my name is Kayla Halleck. I'm currently a sophomore Honors Carolina student and nutrition, science, and research major in Gillings with chemistry and Spanish for the medical professions minors on a pre-medicine track. I hope to one day go into pediatrics, and I also volunteer in the pediatrics unit at the hospital right now, which has really helped me solidify that decision. One interesting thing about me is that I used to live in Yellowstone National Park, which definitely gave me an interesting perspective on adapting to new situations. On campus at UNC, I'm involved in Alpha Epsilon Delta, biology research, Blank Canvas Dance Company, and a couple other small orgs. I want to be a chemistry ULA because of my passion for helping people learn, and also I feel that Chemistry 241 was a huge turning point for me, where I figured out how to effectively study and learn in chemistry classes at UNC, and I think that I can project those skills in order to help other students. One thing I will do to help students develop better study and learning strategies is to provide practice problems and create slides that pull all the content together in an efficient way. This will match the learning objectives and then also share my strategies in analytical, which involved working through the textbook practice problems first, and those were higher difficulty than the exam problems. Another thing I did was making a cheat sheet or brain dump with everything in it from the unit, and then doing a few practice problems in each section right before the exam, which really helped me to succeed. Today we're going to be discussing buffers. Buffers are solutions that remain practically constant in dilution. The pH isn't going to change very much upon addition of very small amounts of strong acid or strong base. The maximum buffering capacity is that where the ratio of base or acid is equivalent to 1. I'm going to be working out a buffer problem that I found difficult at the time in analytical, but through simple strategies helped to work through. Today the buffer problem we're going to do is find the ratio of H2PO4 minus to HPO4 2 minus when the pH is 8.35 for H3PO4. Every time you remove a proton, it's going to make the charge one more negative. The first thing that I would do in this scenario is make a chart and look at the different pKa's. Ka1 is 7.1 times 10 to the negative 3. This is for the most acidic compound, so it's going to be the largest Ka, and reversibly, the smallest pKa. Ka2 is 6.3 times 10 to the negative 8. That's the second most acidic compound, and Ka3 is the least acidic with 4.5 times 10 to the negative 13. I was taught this trick in analytical to write out the reactions from H3PO4 to H2PO4 minus to HPO4 2 minus to PO4 3 minus. Ka1 is from the most acidic to the second most, and so it goes. From here, you can circle the ones you're using. In this case, the question asks about H2PO4 minus and HPO4 2 minus to then plug them into the Henderson-Hasselbalch equation and find your ratio in your buffer. The Henderson-Hasselbalch equation is where the pH is equal to the pKa plus the log of the base, which is the deprotonated compound, over the acid, which is the addition of one proton. In this case, based on the question, our base is HPO4 2 minus because it has one less proton than H2PO4 minus. Then it's simply a game of plugging in the values. You know that you're using Ka2, and pKa2 is simply the negative log of that. You know your pH to begin with is 8.35, so you plug that in here. The negative log of 6.3 times 10 to the negative 8, your K2 is going to be there, and then you're just going to have the log of your base divided by your acid. Simple rearrangement of that equation would get your answer to be 14.1, which is a pretty neutral compound, and that's the ratio of acid to base in the second reaction from H3PO4 to phosphate.
Thank you so much for watching, and thank you for your consideration.